Hi everyone, so today I will explain about chapter 4, stress in beam. Okay, so the learning outcome of this chapter, we have 4 points, which is first, define the relationship between the shear and between the bending moments and also the bending stress. Okay, and then second, we have derive bending the moment formula. Third will be calculate the stress in beam due to bending. For this chapter, we are focusing on the bending. Chapter 5 will be the shear. So for number 4, you will find the neutral axis. So this the example is shown in the videos that part 1 and part 2 for the calculations. You can refer to the other two videos. So introduction, so you can see beam. Okay, so this is the exam beam here. Okay, beam or fracture member, we call it fracture member also, is frequently encountered in structure and machines. So beam that subjected to loads applied transverse way, sideway to the long dimensions and cause the member to bend. So you can see that if this is beam, you can see this is the beam, so it will be transverse way and it will have long dimension here. So when load applied on it, it will cause it to bend. Okay, instead of column, if column is this way, so when you press compression on it, it will not bend this way, but it will compress that way. Okay, so transverse loading causes the bending, and it is very severe form of stretching a structure. So the bending beam goes into the tension stretch from one side and another side will be on the compression. So you will press on it. Okay, when you press a beam on it, so you press like this, so upper side will be compressed when it bend and lower side will be in tension when it pulling out. So upper side will be compression, lower side will be in the pulling out section like this. Okay, so example, you can see since simply supported beam loaded at its third point here will deform into the exaggerated bend shape as shown. So you can see it, obviously there is a bend here. Classify types of beam. You can see beams. Okay, we have so many beams here, and then the support we have pins, roller, or smooth surface at the end. Okay, so you can see this first beam here, simply supported. We have pin support here, roller support here, and the loading on top. Then this is overhanging. You can see this is free end. This one is roller. This is pin here, but then here he will have a hanging here. Okay, no support at here, but then your support is nearby here. So when you cause some load, it will bend this way. And then you can see the third one here. The third one, this is second one. Third one here, cantilever beam. You support at this side. So the moment, and then the support all here, the three reaction force all that here. Okay, and then you will bend and cause this way when you have force on this. So neutral axis. Neutral axis is the axis along the length of the beam which remains unstressed. So where it is the point that it is not stressed when the torque apply. Okay, as you can see, when it bending, the upper part will causing compression and lower part will be tension. But at this neutral axis, it won't affect by the compression or either by the tension. Okay, so it is the region that separated the tensile forces and compression. So this is the borderline of it. Okay, and then bending stress equal to 0. At that point, no bending stress. The position of neutral axis must pass through the centroid of the section. Hence, this position is very important. So we have to determine it. Derivation of the formula. So to establish the bending stress formula, several assumptions are made. So these are the 6 assumptions you can see. Number 1, cross sections of the beam is plane and must remain in plane after the bending, and the beam material is homogeneous, single materials, and obey the hook law. And the material must be free from any resistant force and from impurities, holes or gloves. Okay, and then the bending moment of elasticity in tension must be same for the compression. The moment for elasticity in tension and compression will be the same. and the bending has constant cross section. The cross section won't change, and it is subjected to pure bending. Okay, so due to the actions on the load, okay, so the beam will bend. So consider that the beam into an arc of circle through an angle of theta radians. So AB is on the neutral axis. So the AB is on the neutral axis. Okay, this AB. So R is the radius of the neutral axis, the R. Okay, so by the length of AB equal to R theta, so consider layer of material of distance Y from the neutral axis. The radius of this layer is R plus Y. Okay, so when you substitute it, CD equal to R plus Y times theta. So this layer is stressed because it's become longer and becomes strain, and the strain for this layer, okay, so you know strain, okay, is change in length over original length. So is the length of AB, okay, CD minus the length of original. This is the change in length, and then over AE. So when you substitute the equation into it, you will get the final one is Y over R. Okay, the Y over R. Okay, so Hooke law, okay, also the modulus of elasticity. Stress and strain vary along the length of the beam depending on the radius of curvature. Okay, you know that the E is stress over strain. So when you substitute this, strain is equal to Ry from the previous one. Okay, so you get E is equal to stress times R times over Y. So when you rearrange it, you get E over R is equal to stress over Y. Okay, so fiber stress at distance Y from the neutral axis. Okay, so the stress is equal to M times Y over I. Okay, so you need to remember this formula. At any section of the beam, the maximum fiber stress, okay, is D MC over I, or either equal to MZ. So C is the distance from neutral axis to outer fiber. The outer fiber will be experienced maximum stress. So Z is equal to I over C, the section modulus of the beam. So although the section modulus can be already calculated for a given values of the modulus are often included in the table to simplify the calculations. So E normally will be given, okay, to simplify the calculation. If not, you need to find time to obtain it too. Okay, so these are the theory, and then inside when you have the examples, then you will see it more clearly on how to apply on it. So the value of I, the second moment of area, okay, for a given sections may be determined by formula as in figure. Okay, so the I, let's say for simple shape, already you have the formula, but then for section like I or T, okay, or either the I with this shape. So for this you need to calculate. If the shape is simple like a rectangular or circle, you can just straight away use the formula of I. Okay, so how you can see that the second member are given may be determined as in the formula, but many beams are manufactured with standard sections. Okay, normally the section already having the standard dimensions. So the property you can find it in the standard code. If let's say it's in the design subject, when it's in the design. Okay, so elastic sections modulus, okay, the Z, okay, the section modulus Z is usually quoted for all standard sections, and practically it is greater use than the second moment area. Strength of the beam sections depends mainly on the second module, and the second module of several shapes are calculated as below. So you have also the Z and also the equations here. You can see the Z, okay, the equations are as seen. So the maximum stress in beam, Okay, when you have this bending towards up, okay, bending, negative bending moment, hogging bending. Okay, when it's bending going up, and this one when it going down, okay, positive bending, this is sagging bending. Okay, one is hogging, one is sagging. So we will also have the neutral axis when you have a beam. Okay, this is h/2, you get the neutral axis. Okay, this line is the neutral axis. So y1 or for upper part y2, and then you have the compression and tension due to bending, and this is the point where is the neutral axis, means 0c 0t. Okay, so stress and compression on top is compression by my max over I. So the bottom is my max over y. Okay, but the y is according to the value. So the stress in beam, okay, the effect of stress in beam visualized by consider a beam made up of flat boards stacked on top of one another without being fastened together. So let's say you have a board stacked on top without fastener. Okay, so this one actually for the shear stress will be in chapter 5, but I explain now for the theory together. Okay, so when you stack it up without fasten it together, then load in the direction of normal to the surface of the board. So the lacking of such relative will cause sliding. So when you apply load on it, you can see that this area, okay, might slide. Okay, and deformation in actual solid beam suggests presence of resisting shear stress on longitudinal plane. Okay, so you will have the shear stress on longitudinal plane. So V, the formula you can see that here, V is the shear force. So how you determine the shear force? You need to add A. A is the cross section of the beam for calculation of desired shear point. Y is the centroid. Okay, this one is typing error, supposed to be centroid. I is the moment of inertia. B is the beam or width of the beam. Okay, so when you calculate, this is the shear. Okay, so this one is the figure when you have load applied on the beam. So if let's say you have shear and also bending, so this is the shear diagram, and this is the shear diagram, this is the bending diagram, two different shape. Okay, when you have bending, you will cause this way, compression on top, tension at bottom, and neutral axis you will have zero bending force. But for shear, you will have the maximum, okay, according to the shape. But for this one, you will draw according to shape, and then you can determine the max. Okay, but then on top and bottom here, you can see it's zero shear. Okay, so for pure bending is a condition of stress where a bending moment is applied to a beam without the simultaneous application of axial, shear, or torsional force. Beam that is subjected to pure bending means the shear force in the particular beam is zero, no torsional, no axial force. Mean pure bending only, no other forces, no torsional, no torque, no axial load. Okay, and also the fracture, the bending, is of a beam that is under a constant bending moment. So there's a pure bending only occurs when the shear force is equal to zero. As you can see that here, okay, pure bending in the midsection, you load apply at here, when you have load applied here, and then this section you have no shearing force, only pure bending. Okay, so this equation indicates that for a given allowable stress and maximum bending stress in the sections, the modulus ZE must not be less than the ratio of moment max over the allowable stress. Okay, so if you rearrange, it become like this. So the allowable stress is moment over the ZE. Okay, so this is the example 1. So example 1, so 550 depth and 150 mm width rectangular beam is subjected to maximum bending moment of 750 kN meter. So you have to find first the maximum stress, second the value of longitudinal stress at a distance of 65 from the top surface of the beam. So you need to get the maximum. Also you need to find certain stress at the allocated locations here. So maximum stress in the beam. So this is a rectangular shape, very easy. So stress is equal to my over I. So y for neutral axis for beam, you know, is this over 2. So it's at 125. So here is 125, here is 125. Okay, so it's 125 mm or equal or 0.125 meter. So moment of inertia I is equal to BH3 over 12, BH power of 3 over 12. So you include the you insert the values, so you get the value of I. So when you put into the equation, you get this shear stress, the bending stress value. Okay, so the bending stress, the maximum, is already you obtain 4.8 times 10 power of 8 Newton meter minus 2. So number 2, you want to find the stress at distance of 65 mm from the top. Okay, 65 mm from the top. So y equal to y1. Okay, y1 is 60 mm, 0.6 m. So you use the equation my over I, y1, you substitute the value 750, the moment, okay, the moment is 750, okay, and then you get 750 times 10 power of 3 times 0.06 meter over the I, you get 230 Newton m2. So this is the value of y1, you get y1 from here.